So welcome back, everybody. So yesterday's lecture ended with a discussion of continuity, right, which is a notion that you've encountered before for real-valued functions. And so, superficially, or I mean, I should say, like functionally, if you're just replacing this complex variable with a real variable, this is identical to the definition of continuity that you're used to. And so a function f is continuous at z0. So this is a pointwise definition. So we define continuity point by point. And so it's continuous at a point z0 if these conditions hold. Really, the most important thing to remember is this one. But this limit is z approaches z0 of f of z has to exist. F of z0 has to exist. And this limit is z approaches z0 of f of z is equal to f of z0. So this is the important statement of continuity. And this condition can be restated in epsilon delta form in this way. Okay. And of course, a way of interpreting this is that the image of, basically for any epsilon you pick, the image of, there exists some delta ball such that the image of this delta ball has to be inside the image of this epsilon ball centered at this point f of z0. Okay. So I have to be able to get my values of f arbitrarily close to f of z0, okay, for some fixed z0. Okay. And then, of course, because it's a pointwise definition, I say that f has that property on an entire set if it has that property at every single point in the set. So it's continuous on a set if it's continuous at every single point. Okay. So all of this ports over, right, one-to-one from what you know about real-valued functions. This is the exact same sort of definition. Okay. All right. So now the thing to note, and I'm not going to prove this, I'm just going to write out some quick facts. The proofs of these facts are identical to the proofs of these same facts for the real valued case. So I'll even maybe state them as facts, although these, I could call these theorems if you like. So a sum, so if f and g are continuous, at some point, say z0. Of course, I'm going to put this in parentheses because we could also assume that these functions have the same, say, domain of definition, or at least they're defined on the same set, and we'll say that they're continuous on that entire set. These statements are still going to be true. Then f, say, plus or minus g is continuous at z0. Okay. Next, f times g, right? This is a pointwise definition of the product, right? So, I mean, this is defined to be, right, f of z times g of z, like we talked about before. This is continuous, okay, at z0. You can prove this directly from the definition if you like. Okay, the quotient f over g is continuous at z0 provided that g of z0 is non-zero. Okay, so you can just directly get this from this. These all follow from those theorems of limits, right? So being able to compute limits of sums, products, and quotients, this tells you this immediately. So this follows immediately from our theorems concerning limits of these quantities, right? Okay, and because the limit of a sum is the sum of the limit of differences, difference of limits of product is product of the limits, limit of quotients, quotient of the limits, so long as the denominator is non-zero. These facts about limits directly from the fact that a function is continuous, if that limit exists and that limit is equal to the functional value at that point, then this gives you all of these immediately. Okay. One that also follows in the exact same way, but maybe I'll separate because it's important and it's something that I didn't mention up here. So here's another theorem or that I didn't mention before when we talked about limits, is that a composition of continuous functions is continuous. A composition of continuous functions is continuous. I.e., if you start with f and g that are continuous, this implies that f composed with g is continuous. F composed with g being, so if I have f of z, g of z, this f composed with g of z is defined to be f of g of z. Right? Usual notion of composition of functions. Okay. So again, I'm not going to prove this. Proof of this is done in the textbook, if you like. But this proof is identical to the proof for real valued functions. And so these combined tell us that constructing continuous functions is not so bad, even just starting with polynomials, right? So our motivating example of what what a continuous function is trying to emulate, right, was we had polynomials. We noticed that polynomials satisfied this condition of continuity, and then we asked, like, what other functions do? Well, continuous functions. So this was our definition of continuous functions. And so just starting with polynomials as a basic example of a continuous function, using these, you can, well, a sum and a product of polynomials is another polynomial, so you don't get anything there. But a quotient of polynomials, that's a rational function, right? And so you get rational functions here. Composition, this is going to tell you that if you have two continuous functions, you can get another one just by composing them. And this already gives you a pretty wide range of functions you can get just by, you take two different sorts of continuous functions, you compose them in this way. That is going to give you a pretty wide range of functions you can talk about that are continuous. Okay. Let's state another theorem. So next theorem is if a function f of z is continuous and non-zero, at a point z0, then f of z is non-zero throughout some neighborhood of that point. Okay. So let's think about this for a second. This is, first of all, ask yourself a question. Is this a theorem that is true for continuous functions of a real valued functions of a real variable? And the answer is yes, right? The answer is yes. To think about that in terms of a real valued function, let me get another sheet of paper here. So to think about this, imagine you have a continuous function, and here it is non-zero. So here's a z0, right? So here's f of z0. Okay. Now, if this function wasn't continuous, then its values could be wherever here, right? It could be going along here and then have this single value that's above the x-axis and then continue on its merry way down here. And so this is not continuous. This value doesn't have to be true. But because this function is continuous, how do you go from here to functional values that are, say, 0? Well, you have to do it in this continuous way, right? So this is, even if this is zeroed out after that, there's no other way to get there, even if it was a sharper thing, right? So this doesn't have to be smooth. Here's another example. So here's a point where the function is non-zero. Maybe it does something like this, right? Right, which is not as nice. Okay, maybe it's more rigid like this. But you see, still, there is some neighborhood, right, of this point z0 where the function is not 0. Okay. Because the entire point of continuity is that there are no breaks. Okay, there can be no sudden shift. Okay, that would indicate a break. Okay, so this thing has to continuously slope down, which means that you can find some, and this slope could be extremely severe, right? So here's f of z0. Maybe this thing slopes off like that, but then that just makes my neighborhood smaller. All right, the point is that there exists some neighborhood that I can find where this thing is non-zero. Okay. All right, so this was actually true for functions that were of a real variable that are real valued. Okay. So this is a nice fact, and we're actually going to use this in a lot of ways. So to see that this is true, I can actually prove this. So let's say that it is. Let's say that this thing is continuous and non-zero at some point z0. Okay. Well, what we can do here is that if we think about the definition, right? So if f is continuous at z0 and f of z0 is non-zero, then from the continuity part, let's bring back my definition of continuity real quick. So my definition of continuity, this means that, well, it means exactly this statement, that if epsilon is greater than 0, so epsilon can be any positive number, okay, then the modulus of f of z minus f of z0 is strictly less than epsilon whenever what? Well, for this statement to really make sense and flow, if epsilon is greater than 0, then there exists a delta greater than 0 such that the functional values f of z get squeezed to be within epsilon of f of z0 whenever my z values are squeezed to be within delta of z0. Okay. All right, that's my statement of continuity. Okay. Now, this thing that comes here is directly from this underlined bit that f is continuous at z0. Okay. Well, I also have this assumption that f of z0 is non-zero. Okay. Well, how does this help me? The fact that this is non-zero allows me to do some trickery here. The most important thing to note, like the strong point of this statement of continuity, is that this has to be true for every epsilon that's positive. Okay, and so if I know that that statement holds for every epsilon, the idea is that I want to pick an epsilon that fits what it is I'm trying to show, what it is I'm trying to prove. So if I start out with a statement of continuity, this is a statement that must hold true for every positive number here. So I try to pick one that gets me what I want. So the one that's going to work for us here is, and I should say that when you're doing these proofs, these epsilon delta proofs, the typical strategy is that you might work through the algebra of what you would want epsilon to be first. And once you figured that out, if you wanted to write, a more like concise proof that didn't have kind of that backwards thinking in it, then you could just, discard that and know what epsilon needs to be before you start out. So a lot of times when you're reading epsilon delta proofs going forward in like a textbook or as examples, you'll see a choice of epsilon. You'll be like, where did they come up with that? How did they know that that's what they needed to pick epsilon to be? The answer is that it was worked out in algebra. You didn't see, and then once it's like, oh, this is what epsilon needs to be, then that choice was made at the beginning to make the proof look slick. But it's okay if your proof doesn't look slick when you're doing these things. So, all right, what do I do here? I choose epsilon to be the modulus of f of z naught over 2. This is the one that works. Okay, this is not the only one that works. There's plenty others you could pick. Right, once you know one like this, you can probably guess more. But this is one that works. Notice that this is not 0 because f of z naught is not 0. So that is how we are using that assumption. And so this must be positive. Okay. So this is a valid epsilon to choose, and so restating this means that, i.e., there exists a delta positive such that f of z minus f of z naught is strictly less than the modulus of f of z naught over 2. Okay. All right. And so this is true whenever z minus z naught is strictly less than delta. Thus, if there is some z in the set modulus of z minus z naught is less than delta. So if there is some z within delta of z naught in the complex plane, okay, such that f of z is equal to 0, then if f of z is equal to 0 here in this inequality, that would mean that the modulus of f of z naught is less than the modulus of f of z naught over 2. So this is why we chose this. We could have chosen modulus of f of z naught over 3, over 5, over 10, doesn't matter. Okay. But we have this fact. This is a contradiction, though. Right? This can't happen. So this contradiction arose from the fact that we assumed that there was a z in this neighborhood such that f of z is equal to 0. So this thing that I've boxed, that I'll put a little star next to, this statement must be false. But if this statement is false, then there doesn't exist such a z in this neighborhood. If there doesn't exist such a z in this neighborhood, that means in this neighborhood, for every z that lives in this neighborhood, f of z must be not equal to 0, which is exactly what I was trying to prove. Okay, so I wanted to show you that proof because it's a nice classic use of proof by contradiction. It also uses the definition of continuity. Okay, again, we're not going to do a huge amount. We're not going to do like a ton of proofs with this. We're mostly going to be focused on the computational aspects, but I still wanted to, to show you how it were done because it's nice to warm up with that stuff, because this is ultimately the underlying justification for what's going on in a lot of these theorems. Okay, so one thing to note, and yesterday we showed that, or at least I stated, that taking the limit of a function of a complex variable depends on taking the limit of the component functions, treating them as real valued functions of two real variables, right? So so first of all, the limit of f of z, this depends in a strong way on limits of the component functions u and v, i.e. f of z, right, is f of x plus iy, which is this could be thought of as the real part function u of xy plus I times the imaginary part function v of xy. Okay. And so finding limits involving this function f depends in a very strong way on computing limits of these functions u and v. So similarly, continuity, thus, since continuity is defined in terms of limits, continuity of f of z depends in a very strong way on continuity of u of xy and v of xy. Okay. In fact, we can actually restate this theorem that we stated last time about computing limits of functions of a complex variable in terms of limits of these things. But in fact, we have the following theorem, which is that this function f, so f of z, is continuous at z naught if and only if the component functions u of xy and v of xy are continuous at z naught, of course, which is the ordered pair x naught, y naught. And so, I mean, this is the direct dependence here that ties our notion of continuity of a function of a complex variable to continuity of these component functions, where continuity of these component functions is, in terms of the usual continuity you're used to for real valued functions of multiple variables. Okay. All right. So, again, you might be questioning, like, where do the differences come in? So that's going to come in here very soon in what we do, and it might not be apparent immediately because it will still look very similar. But the difference is going to come in fairly soon here. Okay. I'm going to do one more statement, which is a theorem that you've seen before real valued functions. And this is the following. This is like a corollary of the Min Max Theorem. Okay, and so if a function f of z is continuous on a region R that is both closed and bounded, then there exists a non-negative real number, big M, such that the modulus of f of z is less than or equal to big M for all points z in R. Okay, where equality holds for at least one such z. Okay, this last statement, right, is the Min Max Theorem. But all this taken together is really the Min Max Theorem that you've seen previously. Okay. Okay. Well, how do we prove this? How do we prove this? Well, actually, we can prove this using just old school calculus. All right, so the proof is, note, if f is continuous, then the modulus of f, which is square root of the, it's u of xy squared plus v of xy squared. Considering this as a function of a real valued function of two variables, which it is, this is a continuous real valued function of two variables because all of these operations that I'm doing are continuous in the real. So square root of x, that's continuous wherever it's defined, and there's no issues here because this is all positive, or at least, or it's at, you know, the smallest it could be is 0 here. And so as a real valued function, I have square root and I have a sum of squares. Both of those are continuous. Their composition's continuous. This is a continuous function, so this is continuous because it's a composition of continuous function of real variables. So this is continuous on a closed and bounded set R. When you have a continuous function on a closed and bounded set, it has both a min and a max, and so this inequality holds, and you're done. That's it. And you're done by Min Max Theorem for real valued functions. Now, there are slicker ways of stating what's called the Min Max Theorem, which is exactly this theorem. This is just for complex functions. Okay. So the slicker way involves using something called the Heine-Burrell theorem to restate what it means for a set to be closed and bounded. So remember what the definitions we have of closed and bounded. There is a related concept that is extremely important, but I'm not going to get into right now because the actual definition of it would take me too long to go into, and I don't want to, like I said, I may talk about it later, but I'm not going to talk about it right now. And it's the notion of compactness. Okay, so there's a couple of things to state here. So notes. Okay, so first of all, maybe I'll put a star here. So a function f satisfying star is said to be bounded on R. So if it satisfies this inequality star for all points in a set R, we say that the function is bounded on R. Okay. So this is what it means for a function to be bounded on R, and this is something that we're going to talk about frequently in this course. Okay. All right. So this is the definition of a function being bounded. Secondly, the Heine-Burrell theorem says that thought of as a subset of Rn, okay, so for us we're thinking of R2 here, thought of as a subset of R2, a set is closed and bounded if and only if it is compact. And so by Heine-Burrell we can define the notion of compactness to be closed and bounded. So by Heine-Burrell, okay, which I'm not going to state that theorem, but by Heine-Burrell we say that an R that is closed and bounded is compact. Okay, so I will try in this course to usually use the terms closed and bounded. The reason I bring this up is because what is actually being said here in this theorem is that a function that is continuous on a compact set has an image that is compact. Okay, that is how this could be reformulated. Now, why is that a nicer way of saying it than this? It's not necessarily nicer, but it is telling you more importantly about the relationship between continuous functions and compactness. And compactness is a really, really important notion in math. It might be one of like the most important notions in like analysis of functions in general is the notion of compactness. And so we are going to dance around compactness by having a ton of conditions that we talk about in this course that are essentially equivalent to it or are literally equivalent to it. And so sometimes I will talk about compactness. Many others I will talk about closed and bounded. For us, they're going to mean the same thing. Okay. So, the analog of a compact set, right, in say like a thought of as a one-dimensional set would be like a closed interval, right? So a closed and bounded interval, your typical closed interval. Okay, so we've been building up all of this stuff with continuity. Going back to kind of, where we were headed when we first encountered continuity ever in our lives. The idea was that I defined limits. This allowed me to talk about continuity, which is an important property that functions could have. But really it was a stepping stone because for the computations that I want to do, continuity alone is not enough. Okay, I need more. And what I need really is the existence of a derivative, right? And so that's kind of the thing that motivated me, right? But I had to talk about continuity first because having a derivative at a point is a stronger condition than being continuous at a point, right? So recall your Calc 1 days when you learned that if a function had a derivative at a point, then it had to be continuous at that point. So having a derivative was a stronger notion. That fact is going to hold for us as well. And so now we define derivatives of a function of a complex variable. And so let f of z be a function whose domain of definition contains a neighborhood of a point z0. What's a way to guarantee that this is the case? Well, if you're talking about a function f defined on an open set, right, you're guaranteed to have such a neighborhood. Okay. The derivative of f of z at point z0. So just like continuity, the notion of a derivative is a pointwise notion. Okay, so the derivative of f at z0 is the limit the lim as z approaches z0 of f of z minus f of z0 over z minus z0. Okay. Okay, and we say that f is differentiable at z0 if this limit exists. Okay. All right. When we compute this limit in shorthand, we write that this is f prime of z0. Okay. And this is our definition of the derivative. Note this is very, very similar to the definition of a derivative that you've always seen. Okay. So, of course, in doing computations with this, there's some slick rewriting we can do that is kind of in the style of like a Leibniz infinitesimal here. And so, some thing that we can note, if we define delta z to be z minus z0, we want to think about this as a small but non-zero quantity, right? And so we don't want z to be equal to z0 here. Okay, then we can actually rewrite this f prime of z0 just like we did for functions of a real variable. We can rewrite this as the limit. Instead of the limit as z approaches z0, we can write this as the limit as delta z goes to 0. So this is the limit as delta z goes to 0 of f of z0 plus delta z minus f of z0 over delta z. Right. There we go. Okay. And so, just to be careful here, since my function has a domain and definition and contains a neighborhood of point z0, so it is defined on some neighborhood of z0, then this quantity, f of z0 plus this little bit, this is always defined so long as the modulus of z0 is small enough, right? So this is perfectly well defined so long as the modulus of z0, so as long as the size of, the modulus of delta z, the modulus of, so long as the size of delta z is small, this thing is defined. Okay, and so we can be even slicker here. So we can be even slicker here by rewriting this numerator as delta w. Right, so maybe I'll, here, if I continue on here, I want to keep it on the page. So if we think of this way of expressing a function f of z here, then I can think of delta w as being this quantity that's in the numerator here. So this is like f of z plus delta z minus f of z. Okay. And so then if I want to think of the derivative being in terms of, when we had this as y is equal to f of x and we thought of dy dx, Here, the analogous quantity would be dw dz. Right, so if this is going to be the derivative of my function, this dw dz is going to be the limit as delta z approaches 0 of delta w over delta z. And we have that exact same expression like we got for real valued functions, right? So this Leibnizian way of computing derivatives from these infinitesimal things. Okay. This is useful for just doing basic algebra and checking that this thing works in a way that you might expect that it does. So suppose that, say, for instance, f of z is z squared, our favorite example here. Okay, I want to compute the derivative of this thing at any point. Okay, so I want to compute f prime of z at any point z. How do I do this? Well, at any point z, I can compute the limit as delta z goes to 0 of delta w over delta z of this function. What is that? That is the limit as delta z goes to 0 of, this is z plus delta z squared, right, minus z squared over delta z. So expanding this, you might remember these types of computations from like pre-calc or something. So the limit as delta z goes to 0 of, this would be z squared plus 2z delta z plus delta z squared minus z squared over delta z. So what happens here is z squared cancels. Delta z is a common factor of both terms in the top, so I divide out by delta z here and here. So I get that this is the limit as delta z approaches 0 of 2z, because the delta z terms cancel. Here we're just left with a single power, so this is plus delta z. So the limit as delta z goes to 0 of 2z plus delta z is 2z. Right, but the thing I was computing here is my f prime of z anywhere. Okay, so now I'm immediately suspicious that what is going on is something that I'm very familiar with. Right, we started with function of complex variable f of z is equal to z squared. When I computed f prime of z, this was 2z. Interesting, right? This is interesting to know. This is only one example, but now you are suddenly seeing that, oh, I think I could probably guess what a bunch of derivatives of complex valued functions would be based on this, right? Based on this one example. But let's work out some more using this computation here. So what about, let's do the example of f of z is complex conjugate of z, so it's just z bar. Okay, what would this difference quotient be? So delta w over delta z, what would this be? This would be z plus delta z conjugate minus z bar, right, over delta z. Okay. Well, remember from my algebraic rules of the conjugate of a sum is just the sum of the conjugates, right? So this is z bar plus delta z bar minus z bar over delta z. So the z bars cancel, and this is actually delta z bar over delta z. So I want to compute. So I need to compute the limit as delta z goes to 0 of delta z bar over delta z. What do you think is going to be true about this limit? You can tell me in the chat if you already realize what's happening here. But we've actually done this limit before, or I think we did the reciprocal of this limit. It was the same result here. Okay. And so what do I notice? Right, well, remember, when I'm doing the limit of a complex valued thing, I'm actually allowed to let these complex numbers approach 0 in any way, right? So this limit, I am allowed to let delta z approach 0 in any way. So again, thinking of the plane, I'm going to pick two easy ways. One is I'm going to consider points that are like delta x 0 approaching 0 along the x-axis. And I'm going to consider points that are like 0 delta y approaching 0 along the y-axis. Okay, those are the two approaches I'm going to use. Now, if those match up, well, then I am, happy. It's not enough to prove the limit anyway, but it might give me some evidence for what the limit should be, and then, maybe I can do something. But I'm actually happier if they don't match up, because then that tells me exactly what's going on, right? So let's check to see what's actually happening here. So then, as delta x is approaching, or as delta x 0 is approaching 0, right, along the positive x-axis, then what do I have? Well, note that, I'm just going to write it like this. So I'm going to write the two cases as delta x 0. So in this case, delta z bar is equal to the conjugate of delta x plus I 0, which is just delta x, right? Okay. But delta x, this is the same as if delta z here, of course, is taken to be on the positive x-axis. This is actually the same as delta z in this case, right? Only along the positive x-axis. So they're actually equal. And so then the limit as delta z approaches 0 of delta z bar over delta z is 1, because these things match up. This is delta z over delta z. So limit, I'm not going to rewrite all that. So this is 1. Okay. But on the other, approaching from the positive y-axis, where I have points that look like 0 delta y, this delta z bar is 0 plus I delta y bar, which is 0 minus I delta y, which is what? This is actually minus delta z. All right, so the conjugate of delta z is actually equal to minus delta z. And so when I compute this limit, maybe I'll do it here. So then the limit in this case, let me separate these out. So then the limit as delta z approaches 0 of delta z bar over delta z is equal to minus 1. But this is bad. Okay. This limit has to be computable by doing any approach here, right? So any approach should give me the exact same limit, but it doesn't. There's a mismatch. So approaching from this in this way gives me a limit of 1. Approaching from this way gives me a limit of minus 1. These cannot be reconciled, and so this thing has no derivative anywhere. So it has no derivative anywhere because this limit does not exist at any z. Okay. All right. Okay. And so let's do one more here. Okay, so one more example. Okay. What about if we apply this way of computing derivatives to the real valued function of a complex variable? It's given by the modulus squared. So let's consider f of z is the modulus of z squared. Okay. So let's compute this difference quotient, delta w over delta z. So this is the modulus of z plus delta z squared minus the modulus of z squared over delta z. Okay. Now remember that the modulus of a complex number squared is the same thing as that complex number times its complex conjugate. Oh, a little bit off the page. Right? So we can use that fact here to make this algebra a little nicer to do. So this is z plus delta z times, I can go ahead and split the conjugate. So this is z bar plus delta z bar. Okay, minus z times z bar all over delta z. Okay. So then let's be careful here. What kind of terms do I have? So I have a z bar that cancels the minus z bar, so that goes away. I would have a delta z times z bar. All right, so I would have z bar times delta z. I'm also going to have delta z times delta z bar. Right. And I am also going to have z times delta z bar, so plus z times delta z bar. Okay, and all that is over delta z. Okay, and so rewriting this, canceling out the delta z's where I can here, this is z bar plus delta z bar plus z times delta z bar over delta z. So that's the kind of the crappiest term there. All right. All right. Now, in the previous example, we saw that if we approached from x-axis, positive x-axis, and y-axis respectively, then delta z bar was equal to delta z in the first case, the x-axis case, and delta z bar is equal to minus delta z in the y-axis case, respectively. Right. Okay. And then we can see that we would have two competing quantities here. So in the x-axis case, we would have that delta w over delta z was equal to z bar plus delta z. So in the x-axis case, delta z bar is just delta z. So this is just plus delta z plus z, right? Because delta z bar is equal to delta z. And in the y-axis case, this delta w over delta z would be equal to z bar minus delta z minus z. Okay. Well, what does this mean? Well, I can actually compute both of these limits, right? So I can compute both of these limits. So in both cases, the limit as delta z goes to 0 exists. So I can compute them. So in the x-axis case, let me just remind myself. So here's the x-axis case. What's the limit as delta z goes to 0 of delta w over delta z? This thing goes to 0. This is z bar plus z. That's the x-axis case. What about the y-axis case? So the y-axis case, if you want to go back and check, this limit as delta z goes to 0 of delta w over delta z, this is equal to z bar minus z. Okay. So uniqueness of limits implies that these must be the same. Okay. And so z bar plus z must be equal to z bar minus z. What does this mean? It means that z must be 0. Okay. Thus, f of z equals modulus of z squared only, or cannot be differentiable at any point except z is equal to 0. But is it differentiable at z equals 0, right? We haven't actually shown that. Note, if z is equal to 0, then delta w over delta z is what? This is actually just delta z bar going back here, right? If z is equal to 0, this and this are 0, and so delta w over delta z, regardless of what's going on here, is just delta z bar. So this is equal to delta z bar. Okay. Okay. Thus, this derivative dw dz exists only at z equals 0, where its value, delta z bar in this case, is 0. Okay. So these things are a little different than what you've seen before. Okay, this is actually kind of a strange example here, right? What is it that we just showed in this example? So we have a function. The function in question that we were actually trying to compute the derivative of was the modulus of z squared. We showed that it actually didn't have a derivative anywhere except at z equals 0, and its value there was 0. So what does this show that is a little strange? So this past example, right, this last example shows that a function f of z, I think of it as u plus iv. So this function of a complex variable can be differentiable at a point, say z, which is the ordered pair xy, but nowhere else in any neighborhood of that point. Okay. So this is one kind of neat thing that is shown here. So we have a function that is differentiable at some point, but is not differentiable anywhere else in any neighborhood of that point. Okay. So that's a little odd. The second thing this shows is for this function, we could actually write out exactly what u and v are. So f of z, if that's modulus of z squared, then u of xy is x squared plus y squared, right? And v of xy is the constant function 0, right? Thus, u and v are not only continuous, they have continuous partial derivatives, right? They are continuously differentiable with respect to x and y to all orders, right? Everywhere, right? So these, so thus u and v have continuous partial derivatives of all orders at any point z, which is xy, yet f of z is differentiable nowhere except at 0. Okay. And so this example shows that you cannot tie differentiability of f with differentiability in partial derivatives of u and v in that way. Okay, so u and v having partial derivatives of however many orders you like doesn't tell you, that alone is not enough to tell you that f is differentiable at a point. So the main takeaway here is the following. That's a bad star here. Let me draw a better star. So the main takeaway here is the following. Knowing that u of xy and v of xy have continuous partial derivatives is not enough to guarantee that f of z is differentiable at a point. So here is a key difference, right? Almost everything we've done up to this point, you could basically relegate what's going on to, say, for instance, like continuity, right? Continuity of a function at a point very much had to do with continuity of the component functions, right? In fact, it was equivalent to continuity of the component functions. And that came directly from the fact that limits, right? The limits we were computing of these functions depended on the limits of the component functions. But here, differentiability of the function f is not solely dependent on differentiability in, the Calc 3 sense of continuous partial derivatives of its component functions. Okay, and this is going to be a recurring theme that we stressed. Okay. All right. Now, so this is a key thing to keep in mind when you're trying to think of what exactly you know when you know some fact about the differentiability of a function, or you know less than that and you're trying to figure out whether the function is differentiable at a point. Okay. Now, note also, so maybe I'll continue on the same, was that 3? Yeah, so I'll say 3 here. Note also that f of z is equal to modulus of z squared is continuous. So this is continuous everywhere in the plane, at every point in the plane. Okay, so it's continuous at every point in the plane, does not have a derivative anywhere except at the single point z is equal to 0. Thus, continuity alone does not imply differentiability. Well, that's not too shocking, because that was also the case in real analysis, right? It was the case for calculus. Continuity was a weaker condition than differentiability, so continuity does not imply differentiability. There, differentiability. Okay. Okay, but lastly, being differentiable at a point does imply continuity at a point. Implies continuity at z0. Differentiability is stronger than continuity. Okay. The way that you can do this is the way that you always do this proof. So this is, Calc 1 style. So you look at the limit as z goes to z0 of f of z minus f of z0, right? Well, this is the limit as z goes to z0 of, say, f of z minus f of z0 over z minus z0 times the limit of, as z goes to z0, z0 of z minus z0. So I multiply by z minus z0 over itself. Use the fact that because it's differentiable, this limit exists. Okay, it's just the derivative. And so I can split up these limits all I want to. I can use the product rule for limits, and this gives me, and of course I can only do this when this limit actually exists. So this is f prime of z0 times the limit as z goes to z0 of z minus z0 is 0, and so this is 0. The limit as z goes to z0 of f of z minus f of z0 is 0. That's just another way of saying that the limit as z approaches z0 of f of z is is f of z0. Yeah, so there we go. All right, so that's the canonical proof of differentiability implying continuity at a point. Okay. All right. Now, unfortunately, right at this point, you may be saying, all right, well, before I had a nice understanding of what the derivative was telling me, right? So I was able to draw a picture of this, delta x and delta y in the plane. And so when I was computing these limits, I was able to see that I was limiting the secant lines to become tangent lines, and so this was just giving me the slope of that tangent line to a point, right? And I could interpret that as instantaneous rate of change if my function was like describing position or something. And so, unfortunately, we are not going to have the same sort of interpretation of the derivatives. We will talk about some geometric interpretations of the derivatives, but we'll do that later. But for now, we are just going to ignore that and treat this as we're just computing with this. Okay, we don't care about the geometric interpretation yet. All right. So obviously, it is too cumbersome to compute with derivatives in this fashion of using difference quotients for too long, and so that's something we're going to kind of try to get out of as much as we can. And so to do that, I want to compute some basic derivatives and then show some formulas for differentiation that allows me to compute these derivatives more quickly. Okay, and in fact, most of these formulas, or all these formulas, you're going to be very familiar with. And so you should be happy that this is something that is going to be, second nature to you already, even though we're in this new setting. So I can write this differentiation operator, d dz of f of z, as this is what I mean by f prime of z, and vice versa. So this notation here, what I mean by that is that this is the derivative of f at z. I don't think anybody's going to get confused by that. So some facts. So differentiation facts. These facts follow in the exact same way that they followed for functions of a real variable, because formally, right, these quantities, the way that you define the derivative was exactly the same. Okay, and so what are these differentiation facts? So first, d dz of constant is 0. Okay. Secondly, d dz of the function z is 1. Okay. d dz of constant c times f of z is c times d dz of f, or f prime of z. So I can pull constants through this thing. Derivative of constant is 0. Derivative of z is 1. Okay. We also have your favorite, right? The power rule. Right, so this is d dz of z to the n is n times z to the n minus 1. So this is for n a positive integer. So n is a positive integer. Okay, actually it's fine when n is a negative integer, so long as, the thing that you're raising to the power is actually defined there. So if it's a negative integer, that's going to obviously be in the denominator, so you don't want the denominator to be 0. Okay, what about, say, the product rule, right, or the sum rule, right? So d dz of a sum of functions, right? This is f prime of z plus g prime of z. Okay. What about for products? We have the product rule, this Leibnizian property of derivatives. Having this is what makes a derivative, right? It is that d dz of f of z g of z is f prime of z times g of z plus f of z times g prime of z. This is your favorite product rule from Calc 1, right? Okay. And we have the quotient rule. So let's remind ourselves what the quotient rule was. So d dz of f of z over g of z. What is this? This is low d high minus high d low over low squared, right? So this is g of z times f prime of z minus f of z times g prime of z all over g of z squared. Okay, and this works so long as g of z is non-zero. Right? Okay, now you can derive all of these from that difference quotient calculation just like you would have done like I said in Calc 1. Okay, and then lastly, we have the chain rule. Right. So what is the chain rule? So if f is differentiable at, say, z naught, okay, and g is differentiable at f of z naught, okay, then g composed with f of z is differentiable at z naught, and d dz of g composed with f of z is equal to g prime f of z naught times f prime of z naught. Okay. So this is your chain rule. Chain rule, always one of those things, should have been called the composition rule, because it's just the rule for, taking derivative of composition of functions. But anyway, of course, easy way to remember chain rule is if you rewrite. You can rewrite this in a way using the Leibniz notation that has you canceling out, numerators and denominators to make this make sense. But I'll let you figure that one out. Okay. And so I want to do one example and then I'll be done. So let's do a quick example of using these rules to compute. So let's let f of z be the function that is 2 z squared plus I to the 5th. Okay. I want to compute f prime of z at a generic point. Okay. So the idea here then, of course, is to think about this thing as being composed of the function with the function 2z squared plus I, and that's composed of the function z to the 5th. Right, and so how do I do this? Using chain rule, product rule, and all of those other rules. So what would this be? So first of all, I would take the derivative of, if I view this as something raised to the 5th, this is going to be 5, right, times 2z squared plus I to the 4th times the derivative of what's inside with respect to z, which is going to be 4 times z. So this is going to be 20z times 2z squared plus I to the 4th. Remember, I is a constant here, right? This is a complex constant. Okay. So this is how this works. All right. Now, this provides you with a long list of potential practice problems you can compute derivatives of. But of course, a lot of these, a lot of these are going to essentially boil down to, you remembering your Calc 1 derivative rules. Okay. Now, we will talk very soon about some key differences between what's going on here and for functions of a real variable. So that will become entirely apparent in the next couple of lectures. You'll see exactly what's going on there. Okay. So anyway, so you have homework due tomorrow night, and also tomorrow afternoon I will host some office hours. Same time, like 2 to 3-ish, so swing by if you have questions about any of those things. You can ask. And so So yeah, I will see you all during office hours tomorrow, and that will be that. So anyway, I will see you all tomorrow in lecture, and hopefully during office hours.